Rosenthal. He's from the Caltech, and then he's going to talk about California Legacy Survey, population statistics with expanded catalog, the RV detected exoplanet. So take it away, please.
Thank you. Give me just 1 second to share my screen.
Yep.
Can everyone see and hear me all right?
Not yet. It says started screen sharing, but it's not.
Can you see?
Yeah.
Got it? Okay. Great. Well, hi, everyone. Thanks to the LOC for having me. As Yasuhiro mentioned, I'm Lee Rosenthal. I'm a fifth-year PhD candidate at Caltech, working with Andrew Howard and the California Planet Search team. And I'm here to talk a little bit about the California Legacy Survey, which will use 3 decades of radial velocity measurements, largely from Keck high-res, to explore exoplanet occurrence over a series of papers. So what's the motivation for this work? By studying exoplanet demographics as revealed by today's catalogs, we can shed light on which theories of planet formation are the most viable. Also, looking to the future, as astronomers develop extremely precise radial velocity measurement instruments, this work may also reveal whether stars that host cold gas giants, which are detectable today, are more likely to host small habitable zone planets, which may be detectable with EPRV instruments. So studying planets that are massive enough to be characterized now is both interesting for its own sake and crucial for the planning of future searches for Earth analogs. So a couple of examples of previous radial velocity survey successes. One of these is the Keck planet search, which was published in Coming et al. 2008. This Keck high-res survey of 585 stars found that 10% of all main sequence stars within a certain spectral range, F to M, host a gas giant. Up until this paper, this broad occurrence rate was completely unconstrained, and so this was a really important result in the field. Coming et al. 08 also showed that how planet occurrence varies with orbital period. So the plot here shows the cumulative distribution of planets with respect to orbital period on the top panel and occurrence per orbital period bin on the bottom. And just for a point of reference, 1,000 days corresponds to about a 2 AU orbit for a sun-like star. And the water ice line for sun-like stars, it happens to be generally around 2.5 AU. So this paper also presented the novel result that there is an occurrence bump near the water ice line, which was a key result showing that giant planets are abundant where the protoplanetary disk is richer in solid material. So the observational baseline of this survey was not long enough to explore planet occurrence beyond 5 AU, but it's been 16 years since that survey ended, and we've collected more RVs for those stars since then for the project that I'm describing here. So there's a lot more work to be done to measure occurrence out to 20 years or more, corresponding to 8 AU, well beyond the ice line. On the opposite end of the mass and period range, the Eta Earth survey, Howard et al. 2010, estimated the occurrence of small planets within 50-day orbits of sun-like stars. So this survey used high cadence Keck high-res data. I should have mentioned Coming et al. Also used Keck high-res data to search for and characterize these small planets, and found evidence that contradicted the prevailing theory that there should be a dearth of planets between 5 and 30 Earth masses. So this plot shows the Eta Earth planet catalog in completeness contours, with the region of interest outlined by dashed boxes. And white is more search regions of parameter space that are more complete to searches for planets via RVs, and blue is more incomplete. And you can see that with decreasing minimum mass, there's increase, even without taking occurrence into account, there is an increasing number of planets discovered in this survey. And sure enough, Kepler validated this discovery not long after this paper was published. So moving on to the actual work at hand, the California Legacy Survey is a continuation of these and other CPS surveys, amounting to a catalog of 719 bright stars with radial velocity measurements. Incidentally, almost all of these are bright enough to be ideal targets for EPRV follow-up. Our data largely comes from Keck high-res, which has been taking RVs since 1996. This means that most of our stars have 24-year baselines. We also use data from the APF Levy spectrograph, an automated planet finder that has operated at LIC since 2013, and the Lick-Hamilton spectrograph, which has been operating since the mid-80s and is responsible for many of the earliest exoplanet discoveries. This means that we have up to 35-year baselines, a total of over 100,000 RVs, and 3 years of open shutter time. The median number of observations per star is 41, and the median observational baseline is 22 years. 35 years means that we can confidently detect planets as far out as 10 AU, potentially even further for more massive and eccentric companions. We did careful stellar selection for this survey without prior knowledge of hosted planets to ensure the validity of any occurrence measurements we'll do with this work. We also recognize that this is a historic data set and we want to share it with the exoplanet community for open use as soon as possible. So we are going to publish all RVs, associated activity metrics, and other vetting data, as well as our planet catalog when the first paper in this series is accepted and published. We're currently responding to very constructive referee comments. So what do we do with this data? We look for planets. And in order to construct a planet catalog that we can use to do statistics, we have to search for planets in a uniform, unbiased manner. For that purpose, BJ Fulton, Leah Hirsch, and I wrote an automated algorithm known as RV Search to uncover planet candidates in radial velocity data. It's a fairly straightforward method. It iteratively detects candidates using a likelihood grid search periodogram. The important part is that you can apply it in a uniform way to a catalog of radial velocity data sets. This pipeline also includes an automated framework for doing injection recovery tests, wherein you take your data with your final planet model, inject synthetic signals, and run the code again to see which signals are recovered and which aren't. This produces completeness contours, such as the ones that you saw earlier for the Ada Earth survey, which are essential for measuring population-wide planet occurrence. And as I mentioned, we can run this pipeline on any RV data set with or without knowledge of known planets. So I'm going to release this as an open source Python package alongside the first CLS paper. So we've taken this pipeline and applied it to our catalog. And here are fruits of our labor. We detected 165 known planets in our sample, seen here across the mass and semi-major axis, M sin I and semi-major axis range, as well as 15 new planet candidates that made it through our vetting process. And vetting for new candidates included a uniform study of stellar activity metrics and instrument systematics. So this should not be taken as a 100% complete certain catalog, but rather a catalog for which every planet candidate passed a uniform set of vetting metrics. But more work can obviously be done once this catalog is put out into the public. So anyway, this plot shows our catalog against the backdrop of median search completeness for our survey, where gradation happens in degrees of 0.1 in completeness. And we can see the same effect first produced in Howard et al. 2010, as well as the Harps study of Mayor et al. 2011, where within 0.2 AU 50 days, you can see increasing number of planets with decreasing mass and even decreasing completeness. So also, once we complete a search for a given star and have a final model of number of planets, we use Monte Carlo methods to generate posteriors for orbital parameters and M sin I. This matters substantially for long period planetary and brown dwarf candidates that have unresolved orbits. So for example, the 4 green dots up in the top right of the panel, where green dots represent new candidates, are all either new discoveries or previously known trends that now have significantly constrained orbits. But the orbits may have a wide range of possible orbital periods and masses. So we can combine those completeness contours that I showed with our planet catalog to do all sorts of different occurrence measurements. For instance, while the first CLS paper will just report the stellar and planetary catalog, the second paper will return to the work of Cumming et al. 08 and measure occurrence with respect to orbital distance, this time far beyond the water ice line. BJ Fulton is actually leading this work. I'm second author, and we'll publish this alongside the first CLS paper. So this plot here shows occurrence with respect to semi-major axis, and it should be noted that this is a preliminary result. We're still tuning our models and our occurrence calculations, but we confidently measured an occurrence fall off beyond 3 to 5 AU. So this breaks from an extrapolation from the power law occurrence fit in Cumming et al. 2008, which was not meant to be extrapolated beyond 3 to 5 AU, but this means that planet occurrence actually falls beyond the water ice line. So we don't know what this means yet. It might say something about inward migration of gas giants. It might say something about paucity of in situ cold gas giant formation because the gas or planetesimal density is just lower beyond 3 to 5 AU. And yeah, so this is this is in tentative agreement with the results of Fernandez et al. 2019 and Wittenmeyer et al. 2020 that occurrence either holds steady or falls off beyond the water ice line. So for the following paper, we'll use our homogeneously generated planet catalog to compute conditional occurrence of outer gas giants given the presence of inner super-Earths. Because most of our data sets are sensitive to Jupiter mass planets out to several AU. Even our sparsest and shortest baseline data sets are 50% complete to a Jupiter mass planet at 3 AU. So shown here are all of the planets belonging to systems that host both a detected small inner planet and a detected large outer planet with associated completeness contours for that sample of stars. So the trickier measurement is the occurrence of inner small planets given the presence of outer gas giants, since most of our data sets are not sensitive to objects below 20 to 30 Earth masses. However, most of our data sets that host gas giants do have enough RVs that they are sensitive to close-in planets above 15 to 20 Earth masses. So using our completeness contours, we can place a lower limit, important to say lower limit, on this conditional occurrence rate. And we can also independently compute these separate probabilities and use Bayes' theorem, shown below just for fun, to see whether they match up. And this is very much work in progress. But one preliminary finding is that small planets rarely are partnered with Jupiter mass planets within 2 AU. This isn't, I'm not sure how novel of a result this is, but perhaps this means something definitive about how close in gas giants suppressing small planet formation. We need to do more follow-up work to elucidate this. So I'm also interested in learning about planet formation by studying eccentricity distributions. And a lot of interesting work has been done on this over the past few years, including Van Eilen et al. 2019 study of small transiting planets and Buller et al. 2020's Astrometric study of giants and brown dwarfs. So these papers use hierarchical Bayesian methods to jointly fit the eccentricity posteriors of many planets. So I've begun to do a similar study with the CLS sample of giant planets with over 110 giants and a handful of substellar companions, most of which have tightly constrained eccentricity posteriors. So this plot just shows a comparison between multi-giant systems on the top and single giant systems on the bottom. And just a preliminary result, we see a long tail for single giants that's not present for the multis. And there's a lot more work to be done here to elucidate how significant this is and what it means, but it could say something meaningful about the excitation mechanisms for giant planets. And I know I'm running over, but just one more potential study that we'll be doing with this work is after collecting a few more years of data, we'll publish an update to the longest period and most eccentric orbits in our catalog, shown here, including two candidates to be published. These are candidates rather than confirmed. This is just because representative planet catalogs matter, particularly for long period planet occurrence measurements as we push into the regime of direct imaging surveys. And that's my time, so I'll take questions, and thanks for listening.
Hey, great, yeah, nice talk. Yeah, that's really nice talk. And then if you have a question, just type in Slack channel. And then before waiting the question from the audience, I'm gonna, as a chair, I'm gonna ask you a question. So, so what's is there any difference between RB planet and the transit planets?
Do you mean difference in what our occurrence measurements are, where they overlap?
Yeah, something like that. Actually, I know that especially for the hot Jupiter, I think the RB planet, the occurrence of the RB planet is slightly higher than the Kepler planet, right? So.
Yeah, that's a great question. I'm actually not entirely sure that a quantitative answer to your question. I can say I've been doing a little work to look at hot Jupiter occurrence in our survey, and I'm actually still finding slight disagreement with previous results. So I think I need to do more work with that to figure out methods before confirming whether it's different from transiting planets. One thing I can say is that we're interested in taking this catalog and the small planets in it and comparing that catalog to the planets recovered by Kepler and K2. And the numbers here, both in terms of number of stars and number of recovered planets, are obviously different. But I'm curious to use mass-radius relationships to try to pin those to each other and see whether they match up naturally or whether there's some discrepancy. Does that answer your question?
Yeah, sure. Sounds great. Yeah, and then okay. So the one question, so when you inject a fake longer period or longer separation planet into your RV search, do you still see a drop off of the occurrence at the separation beyond the 3 AU?
Yeah, that's a great question, and it's a really important one. So the way that we currently do the injections is we inject, widely across, we uniformly across minimum mass and semi-major axis. And I think relevant to this question, we pull eccentricity from a beta distribution. There was Kipping et al. 2013 sort of did a fit of an eccentricity distribution to all RV discovered planets. And just pulling injections from that distribution, like, it's not right, but it's less wrong than pulling purely from circular orbits, right? Because if you pull eccentric planet, if you inject eccentric planets, you're more likely to recover those long period than circular orbits. So the actual answer to the question is, you still see the fall off. It's tentative, and I've actually, over the last couple of weeks, been doing work with BJ to determine how steep the fall off actually is. What we can say for certain is that occurrence doesn't continue to increase. That's absolutely not the case. It's either stagnant or falls off with appropriately large uncertainties as you get into the regime where you see only a couple planets and your completeness is extremely low, like 20% or lower.
Okay, great. Actually, you got one more question, but due to time, I guess we're gonna cut
this. I can answer it offline. I'll check out.
Right, yeah. Okay. Again, yeah. Let's thank you.
Thanks very much.